Good morning, everybody. And today I'm going to present our new results on quantum simulation and quantum annealing with superconducting circuits using the Floquet technique. And this was done at the Niels Bohr Institute in Denmark together with Anders Sørensen. So there were many advances in superconducting circuits going through decades, but today I'm going to talk mostly about recent advances coming up last year. So these are chips of a rather small system but highly coherent transmon qubits which allow for quantum computing in the digital fashion. But here I will be mostly interested in quantum simulation with this system and this application to quantum annealing. So let's take a transmon chain, and the Hamiltonian of this in rotating frame will be nothing else but just a Hamiltonian of bosonic oscillators with nonlinearity and nearest neighbor hopping. So if we project it into lowest subspace, we will have this correspond to spin 1/2 Hamiltonian with magnetic fields which can be controlled in time, but the coupling will be of xx plus yy time, so it will be fixed to isotropic xy model. And that, of course, can be used for to demonstrate digital simulation with high-fidelity C-phase gates. However, it has limited possibilities for analog simulation. So this is just a single point in the parameter space. And for using this Hamiltonian, you can actually go and simulate something with digital, and it was shown to be universal. Of course, it will be superior if we implement the quantum error correction. However, it's still expensive in the sense that you need to trotterize the dynamics. So once you do that, of course, the fidelity of simulation won't be huge, and especially it's limited by current capabilities. Once you can engineer your Hamiltonian and do this analog approach, you get the continuous dynamics without on and off errors. You don't have trotter errors, so in some sense, the fidelity will be much higher. But typically, it requires this device which is designed for your problem. So it's very difficult to configure, and there is still an issue of error correction for this kind of simulation approach. And I want to ask, is there an alternative way how we can do it, trying to keep both advantages of both approaches? And one way will be to do something we call it the Floquet quantum simulation. So I want to introduce a simple example, at least, how we can switch from xy interaction of transmons to the Eisen interaction. And this can be imagined with just 2-qubit system where we have xs plus yy coupling, and we put magnetic field on the second qubit. It rapidly oscillates in time, and what happens, it will simply do nothing with the first term, so that will be just the Eisen term we want, but it will rotate the second spin such that there will be yy coupling and yz coupling, which again rapidly oscillates in time. So if we do everything right, and we consider this frequency of oscillation to be large, what we can do, we can average these terms to 0, and it's easy to imagine that yy minus yy will eventually cancel out. So with this, we will be left with effective Eisen term. From this hand-waving argument, I can go to a more detailed theory, saying that what we need is a time-dependent Hamiltonian with a static term and large periodic term with a Floquet period t and inversely proportional to the frequency of oscillation. We can eliminate this term with a unitary transformation, and this rotating Hamiltonian later should be averaged out. So the unitary dynamics now, what matters is actually the periodic unitary, and at the integer number of periods, it will correspond to effective time-independent Hamiltonian, which is also called Floquet Hamiltonian, given by the infinite number of terms. First one will correspond to the period averaging of your time-dependent Hamiltonian. Second term will correspond to a double integral with a commutator, and the higher order terms will have a similar fashion, can be written in similar fashion. So the important message is that while this is just period averaging, the first order correction will have 1 over omega per factor. So if omega is large, then we are left with a single term, and this indeed will be the Hamiltonian we want to simulate, while other terms will just contribute to errors. Now let me construct the transverse Ising model as an example of this Floquet simulation. So we put on even sublattice this oscillating magnetic field, and what it does, it kills the YY interaction term. Additionally, we want to put the transverse magnetic field on sublattice, which can be static, and we will need a time-dependent magnetic field for even sublattice. So a little bit more technical, what we will do is that we do the transformation for even sublattice and define the function g of t, which will be just integral of magnetic field. Next, the rotated Hamiltonian will actually have a bunch of terms. Some are useful and some are not. So when we average it over a period, we get the Ising term, which is the one we want to see. Then we can cancel, due to choosing properly g of t, we can cancel zy coupling. Same is possible to do for yy coupling. We have a static term for odd sublattice. In the same fashion, we can cancel the emergent y field. And having the time dependence of original magnetic field, we can average it to some constant value. So in the end, we will be left with something which resembles the Ising Hamiltonian. So to do so, I will choose cosine modulation of magnetic field. And the important part is that the amplitude of this magnetic field should scale proportionally to omega. And this omega should be much larger than the energy scale of two-body interaction. If we do so and choose the magnetic field to be time-dependent, then for lambda equal to 0 order of Bessel function, we can realize exactly the Floquet Hamiltonian corresponding to transverse Ising model. Now, I want to actually simulate something with this approach, and I also want to compare it with existing approaches. So for this, I picked up the digital one, which is, of course, the straightforward way to implement transverse Ising model with transforms. And with this, what I need is to apply xy unitary on 2 qubits, then do the same, rotating it around x-axis for 1 qubit, such that I get a minus sign instead of plus, and add transverse magnetic fields on all qubits. So this single trotter step should be repeated many times, and if we imagine infinite number of times, this will correspond to unitary dynamics of transverse Ising model. As a proof of principle calculation, we can imagine just 4 qubit chains with no decoherence. We will start with initial state, which is highly excited, and measure magnetization. So the solid line just shows what you will get with analog simulation, and the dots correspond to stroboscopic periods of Floquet simulations. And we can see that there is a reasonable agreement. What does it mean? Reasonable can be quantified by the infidelity of simulation. So the infidelity for Floquet simulation actually grows in time, and this we can understand as appearance of this higher order terms which we neglected. For the digital approach, we can see that infidelity grows more dramatically due to the fact that we trotterize the dynamics. And here I must explain that to compare these approaches, it's actually very tricky because they are different. So what I do here, I say my frequency of oscillation is fixed, so my simulation time is fixed, and I can calculate the number of stroboscopic periods. And naively, we will imagine that the number of trotter steps will be the same as the number of stroboscopic periods. Fine. So we can see that Floquet approach works for a dynamic simulation, but let's look at something more useful. And the useful thing will be to actually do annealing with this Hamiltonian in Floquet basis and prepare some, for example, cluster states. So if you start with this Hamiltonian, we can anneal it to something which will be GAZ in the X basis. And with continuous annealing, we can go up. Here I chosen time to be smaller than we need for unity fidelity, just such that the oscillations here look much nicer. So if we anneal continuously, we can also imagine the same annealing in the time with the time-dependent Hamiltonian. So here I will present the numerical simulation of the full time-dependent Hamiltonian given by this highly oscillating terms. But what is important is that at stroboscopic periods, the dynamics they will correspond exactly to the continuous annealing. So, for example, with this technique, we can prepare the GZ states having original XY type of Hamiltonian. Fine. Let me next quantify how well can we do annealing with this technique. And for this, I will need to fix the frequency, fix the coupling, and also total annealing time to some larger value. And there will be a question of, if I have a number of Trotter stroboscopic periods fixed, what should I put for Trotter steps? This can be understood from the following picture. In Floquet approach, what we have is a fixed 2-qubit coupling. So it's always on. We don't manipulate it. But what we do, we modulate the magnetic field on each qubit. However, for the digital approach, what we need to apply, first of all, XY interaction 2 times on first pair of qubit. Then we will need to do it separately on the second pair of qubit. So this is done sequentially, and already we cannot achieve the same number of Trotter steps as stroboscopic periods. Additionally, we will need to have the separate magnetic field. So in the end, it will be 3 times as small. And keeping this in mind, as a function of number of qubits, the infidelity, of course, it grows for the continuous annealing since I measured to the target state. It also grows for Floquet annealing and has this shift. But with the digital approach, what happens is that it actually performs very well for the small number of qubits, but at the later stage, it grows more dramatically. And this can be quantified using the following slide. So first of all, the infidelity of Floquet approach is highly sensitive to the frequency at which you modulate. So ideally, you want to sit at the very large modulation frequency, but this comes at the price that the magnetic field you use, the amplitude should be large as well. And that's, of course, will be limitation since we cannot put it in infinite. For a digital approach, what happens if we trotterize the dynamics is that for a small number of Trotter steps, typically you cannot get large fidelity of simulation, while for a large number of Trotter steps, it nicely converges to some very small infidelity. So here is, of course, very important where do you sit in the terms of parameters of your system, and it has a kind of threshold-like behavior. Finally, I would discuss briefly the imperfections of the scheme. So, of course, it will be decay and decoherence, which should be treated carefully, but these are same for annealing and in Floquet basis and in the digital fashion. Then the fact that we need large magnetic field actually produces another type of error, since we drive not only 0-1 transition, but also 1-2 transition in anharmonic ladders. And here the anharmonicity becomes very important to prevent the leakage out of logical subspace. And for realistic parameters, if we take the frequency to be 20 times as the coupling constant and take anharmonicity of the transmon qubit, then we can imagine that in 2 microseconds we can anneal, let's say, 4-qubit chain to 0.99 fidelity with analog approach, and the Floquet approach will actually be very close. So it is possible, and moreover, with coherent flux qubits, I believe this can be highly improved. Finally, so far I just benchmarked the transverse Ising simulation, but the real goal here is to go to generic simulations where we imagine different magnetic fields on each qubit, and with this we can organize anisotropic couplings and general Hamiltonian. So the first example I already worked on is the modulation even on sublattice along the arbitrary static axis. With this, what we can get is this general type of Hamiltonian, which is XYZ type being non-stochastic. And this will have, of course, implications for annealing with this type of Hamiltonians. What can be done, what cannot be done is these coefficients are not independently controlled. So to do so, we will need to consider arbitrary rotating axis, and this is under development. Finally, the main motivation was actually to go to a cluster model with these couplings, and if we allow for additional tuning knobs, this will be possible in future. So finally, let me conclude that I considered the different approach to start with the static considering time dynamical Hamiltonian, which can in configurable way model the effective Hamiltonian of the system of interest. It can be optimized such that you use your resources wisely, and possibly this can also be applied to non-stochastic Hamiltonians. And I already tried this approach, showing that indeed you can anneal with high fidelity to this Hamiltonian. So thank you very much for attention.
Right, we have time for a couple of questions. So I have a question. I mean, you said that these frequencies, they have to be very large compared to the coupling, basically. But is that true, or they have to be very large in comparison with the global energy scale of the problem? What I mean is that if you have a problem that, with the n qubits, right? I mean, as you increase n, do you have to increase the magnitude of these oscillations?
I guess the general restriction is really what you put in front of the Hamiltonian here. So typically, this will be the only relevant energy scale which matters if you start with XX plus YY Hamiltonian. Mm-hmm. And the Floquet approach will work well. Like the infidelity will not grow with the number of qubits. So I guess here what you really need to think is that J is small for nearest neighbor interaction. I actually don't know what happens if you allow for larger connectivity.
I mean, I was worried because, in principle, you want to prevent these oscillations of generating transitions between different states, right? So you would like to avoid, going from the lowest energy level to the highest energy level, if you want. And that's difference of energy is given by the global magnitude of the...
So here, I guess, the trick is that omega should be much larger than J because you want to consider the Floquet period to be much smaller than everything what happens in the Hamiltonian. So if you can to satisfy that, you are fine. I mean, you want to period average, and nothing should happen at this time scale.
Right. So any other questions? All right, so if not, let's thank Oleksandr again.